Picture this. Our seemingly barren moon isn't just a dusty rock orbiting Earth. It's been quietly gathering precious droplets of our planet's atmosphere, including water and other essential ingredients for life, thanks to an unexpected cosmic delivery system. But here's where it gets intriguing. Earth's magnetic field, long hailed as our protective shield, might actually be playing a key role in guiding these particles away from us and onto the lunar surface. Intrigued? Let's dive deeper into this groundbreaking discovery that could reshape our understanding of planetary connections. At first glance, the moon appears arid and devoid of life. Yet emerging research reveals it may serve as a timeless repository of Earth's atmospheric history. Scientists have found that minuscule particles from our planet's air are piggybacking on the solar wind, embedding themselves into the moon's soil. These tiny travelers could include vital supplies like water, nitrogen, and other compounds that support life. Even more fascinating, and the part most people miss, is the role of Earth's magnetic field. Traditionally viewed as a barrier against space's harsh elements, new evidence suggests it might instead act as a conduit, directing some of these particles outward into space and toward the moon. This challenges long-held beliefs and opens up a debate. Is our magnetic field more of a helpful guide than a strict guardian? This research, spearheaded by experts at the University of Rochester, tackles a long-standing mystery. Why do lunar samples contain higher levels of certain volatile elements than what the sun's solar wind alone could reasonably provide? By analyzing preserved particles in lunar soil and using sophisticated computer models, we can reconstruct the evolution of Earth's atmosphere and its magnetic field over time. Integrating data from lunar soil particles with advanced simulations allows us to map the historical journey of Earth's atmosphere and magnetic field, explains study co-author Eric Blackman, an astrophysicist. We've had direct access to the moon's surface through the Apollo missions, which brought back samples of its regolith, the loose, fragmented layer of soil and rock on the moon's surface, in the 1970s. These grains are packed with volatiles, such as water, carbon dioxide, helium, argon, and nitrogen, which researchers have meticulously studied. Some of these come from the solar wind bombarding the moon, but the quantities, particularly nitrogen, exceed what's expected if the sun were the sole supplier. In 2005, researchers from the University of Tokyo proposed a bold theory. Perhaps some of these volatiles originated from Earth's atmosphere, but only during ancient times when our planet lacked a strong global magnetic field. The reasoning was simple yet compelling. If a magnetic field blocks charged particles from escaping, then Earth's air shouldn't seep out to the moon once that field forms. But here's where it gets controversial. The latest study overturns this notion, demonstrating that even with a powerful magnetic field, atmospheric particles can still find a way out, and the field itself can facilitate their journey. To explore these competing theories, the team employed high-tech simulations, comparing two extreme scenarios: an ancient Earth without a magnetic field amid intense solar wind, and a contemporary Earth with a sturdy field and milder solar conditions. They posed a straightforward query: which setup best matches the particles observed in Apollo samples? Surprisingly, the contemporary Earth model outperformed the rest. In this scenario, solar wind particles collide with the outer edges of Earth's atmosphere, dislodging neutral and charged particles. Instead of functioning as an impenetrable barrier, the magnetic field behaves like a series of tracks or rails, steering charged particles along curved paths that stretch thousands of kilometers into space. Some of these field lines extend far enough to usher freed atmospheric particles toward the moon's orbit, where they gradually accumulate on its surface. It's not a sudden flood, but a gentle, ongoing sprinkle that unfolds over billions of years, building up a subtle yet significant deposit. For beginners curious about this, think of it like how a fan blows dust out of a room through an open window. The magnetic field isn't stopping the flow, it's channeling it in a specific direction. If Earth has been steadily dusting the moon with these particles, the ramifications are profound. The lunar regolith transforms into a preserved chronicle of our planet's atmospheric shifts. Each layer of embedded particles records a snapshot of changes, from the movement of continents and volcanic eruptions to the rise of life and, more recently, human industrial activities. This archive holds immense scientific value. Rather than piecing together Earth's often chaotic geological records, Scientists could examine lunar layers for insights into past climates, ocean compositions, or major atmospheric milestones. And since the moon lacks weather, tectonic plates, or living organisms to disturb its surface, it acts as a pristine time capsule. Practically speaking, this could benefit future explorers. The slow buildup of Earth-derived volatiles, like water and nitrogen, enhances the moon's potential as a resource hub. If astronauts can extract and refine these on-site, they might produce air, drinking water, and even fertilizers locally, slashing the cost of supplies from Earth. Even small reserves could make a lunar base economically viable, turning a distant dream into a feasible reality. The study's methods also offer a broader lens for studying other celestial bodies. Take Mars, for example, which once boasted a magnetic field and a denser atmosphere but now has neither. By understanding how magnetic configurations, solar wind intensity, and atmospheric chemistry interact across time, we can better answer pressing questions. When did Mars dry out? How quickly did it lose its air? And under what circumstances do planets retain enough volatiles to foster life? Our research could extend to grasping early atmospheric loss on worlds like Mars, added co-author Shubhankar Paramanik. Examining different eras reveals how these interconnected processes influence a planet's ability to support life, he noted. In the grand scheme, this discovery doesn't dismiss the solar wind's role in delivering volatiles to the moon. It simply adds a new chapter where Earth isn't passive. With the right magnetic setup and solar dynamics, our planet can release minute traces of its atmosphere via magnetic pathways that curve toward the moon. This process is subtle, accumulative, and spans eons, embodying the slow-motion physics that etches marks over geological ages. Looking ahead, the next steps are clear and exhilarating. Scientists aim to collect targeted samples from shaded and illuminated regolith at varying depths and locations. They'll also use isotopic analysis, a technique to identify unique fingerprints of elements, to distinguish Earth-sourced materials from those from the Sun or comets. Upcoming missions will view the moon as both a treasure trove of resources and a historical document. For as long as humans have admired the moon's glow under the stars, it has been mirroring us, not just by reflecting our light, but by archiving the subtlest fragments of our air, particle by particle across billions of years. The study appears in the journal Communications Earth and Environment. Enjoyed this article? Sign up for our newsletter for more captivating pieces, exclusive insights, and the newest developments. Discover more on EarthSnap, a complimentary app from Eric Rawls and Earth.com. What do you think about this? Does the idea of Earth's magnetic field aiding the escape of life-sustaining particles to the moon make you rethink planetary protection as we know it? Could this subtle leakage influence how we approach space exploration or even the search for life elsewhere? Do you agree that the moon's role as Earth's atmospheric archive is a game-changer? Or do you see potential flaws in the research? Share your opinions and spark a discussion in the comments. We'd love to hear your take.